Right now, the entire AI industry is basically obsessed with throwing more hardware at problems.
Yeah.
Like you want a smarter model, you just buy bigger clusters, you scale up the parameter count, and you eat the massive memory footprint.
Right. It's just brute force.
Exactly, brute force. But what if the key to unlocking massive performance gains for, complex reasoning wasn't more GPUs, but literally changing a single denominator in your code from a 4 to a 2?
Which sounds completely made up, but it's real.
It is. Today on AI Paper Slop, we are looking at a paper that is just an absolute masterclass in getting more out of what you already have. It's called DeepLoop, Depth Scaling for Loop Transformers, published by researchers from Princeton and UCLA.
And for the AI researchers and ML engineers tuning in, we're going to give you the core insight right now. So the paper focuses on loop transformers.
Right, which are models that increase their effective depth by reusing the exact same physical blocks for multiple rounds.
Exactly. But the researchers identified a massive structural catch with doing that. Reusing parameters completely breaks standard residual scaling rules, like DeepNorm.
Because the gradients are aggregated and then read across multiple visits, right?
Yes, and that creates a severe training instability they call the tide depth effect. But DeepLoop fixes this with a one-line architectural change. They mathematically prove you just need to increase the residual scaling exponent from 1/4 to 1/2.
So, okay, in mathematical terms, by setting the skip scale alpha to the square root of 2n and the initialization gain beta to the inverse square root of 8n, DeepLoop just strictly improves validation loss and downstream accuracy on GPT-2 style models.
Yeah, and it goes beyond standard language modeling. When they applied it to hierarchical reasoning on the ARC-AGI benchmark, it boosted performance by over 3 percentage points.
Which is huge. And crucially, all of this happens without adding a single new learned parameter to the architecture. Not one.
Right. To put those formulas into plain English before we, go any further, they proved that you have to scale your network based on the number of times a block is visited, not just the physical size of the network itself.
So if you loop it more, you have to squash those initial weights down harder so the signal doesn't explode.
Exactly.
Okay, I mean, changing a 4 to a 2 on a whiteboard is beautifully simple.
Right.
But AI is littered with elegant math that completely falls apart the second you spin up a training run.
Oh, absolutely. The graveyard of elegant math is very crowded.
Right. So to really understand why this actually works, I want to make sure I'm wrapping my head around the baseline mechanics first. Like, why are we even talking about loop transformers right now?
Well, it comes down to a massive shift in how we think about compute. Right now, there's a huge trend toward recurrent depth and test time compute models.
Like universal transformers or Albert, right?
Yeah, exactly. Yeah. Those. The goal there is to decouple a model's expressivity from its memory footprint.
Right, because normally if you want a 100-layer transformer, you literally have to store 100 unique layers of weights in your VRAM. And VRAM is, like, always the ultimate bottleneck.
It is. But with the loop transformer, the mechanics are highly efficient. A model stores a small number, let's just call it K, of physical blocks.
And each of these blocks has your standard attention and feed-forward sublayers.
Right. But instead of just passing the data through them once and being done, the model loops the data through those same physical blocks for R rounds.
Okay.
So you end up with an unrolled effective depth of N, which is K times R, while only paying the memory cost to hold K blocks.
So you're spending extra sequential compute at test time to generate richer representations, but without inflating your parameter count at all.
Exactly. It's incredibly memory efficient.
Okay, that makes sense for memory. But here's where my mental model of the optimizer gets kind of stuck. Think of a standard untied transformer like a relay race.
Okay, I like that.
Every layer is a distinct runner carrying the baton. And because they are distinct, they get their own isolated training, their own specific diet, and, their own specific gradient update based solely on their single leg of the race.
Right, they just run their one segment.
Exactly. But a loop transformer is like taking a small team of runners and making them run multiple laps. So if I'm an optimizer, how does making the same runner run multiple laps change the way they recover and improve from the race? Like, how does this weight sharing fundamentally violate the standard optimization assumptions?
Your relay analogy is actually the perfect way to visualize the flaw in standard scaling. So standard residual scaling, specifically DeepNorm, was a breakthrough because it allowed us to train very deep post-layer normalization transformers.
Which were notoriously hard to train before that.
Very hard. DeepNorm did this by bounding the first-order effect of parameter updates. But its entire mathematical foundation assumes a fresh runner for every single lap.
So it assumes total independence.
Yes, 100% independence. If you have an unrolled depth of n, you have m equals 2n residual sublayer visits, one for attention, one for the feed-forward network per block.
Okay, got it.
DeepNorm assumes every single one of those m visits owns a distinct parameter tensor, contributing exactly one independent update term during backprop.
So going back to the runners, if you give a fresh runner a single cup of water after their lap, they are perfectly hydrated. They're fine.
Exactly. But if you make the exact same runner run 5 laps and you hand them 5 cups of water all at once, they are going to choke.
Because in a loop, it's just one runner taking all the updates.
Precisely. The math of weight sharing completely shatters the assumption of independence.
Okay, let's unpack this and look at the mechanics in the actual backward pass, because the paper calls this the tide depth effect. It sounds like an aggressive feedback loop.
It is. What's fascinating here is how the gradients couple together. When a physical sublayer is visited r times in a loop, its optimizer update isn't independent.
It aggregates the gradients from all rounds into one single massive shared update.
Exactly. And then in the next forward pass, that single updated tensor is read r times by those exact same visits.
It is written by many visits and read by many visits.
Yeah, it creates this echoing compounding of the gradient signal. And to formalize this, the researchers introduce a vital metric called the visit alignment coefficient. They denote this as Kappa R.
Kappa R. Okay, and what does that measure?
It measures how aligned the visit-wise gradients and sensitivities are across the different rounds.
What does aligned actually mean in this specific context? Like, are the parameters just being pushed in the exact same direction in vector space on lap 1 as they are on lap 3?
That is a great way to think about it. If the network is doing totally different representation transformations on lap 1 versus lap 3, we say the visits decorrelate.
Okay, so they're doing different jobs.
Right. In that scenario, Kappa R is basically on the order of 1. The looped model behaves like an untied model, and DeepNorm's standard math works perfectly fine.
Ah, okay.
But if the visits are highly aligned, meaning the network is relying on similar transformations across the loops, which they call the conservative regime Kappa R scales linearly with the loop count, R.
Wow, okay, so the shared update acquires an entire additional factor of R just from the gradients pointing in the same direction.
Exactly.
So if I'm looping a block 10 times, that update is essentially 10 times stronger than the standard scaling math expects it to be.
And that completely breaks the DeepNorm bound. DeepNorm relies on a scaling exponent of p equals 14.
Okay.
That specific fraction comes from the untied stability condition. That condition dictates that m times the ratio of beta over alpha squared must remain on the order of 1.
Right. But the moment you introduce that tide depth effect, the bounding requirement actually changes.
Yes. You now need m times kappa r times the ratio of beta over alpha squared to remain stable.
Oh, I see the collision course here. So if kappa r is growing with your loop count r, while your physical depth k remains fixed, keeping your exponent at 14 leaves a residual growth of r in your perturbation bound.
Exactly. The water cups keep piling up.
The network just becomes fundamentally unstable. The signal explodes.
It does. So to keep the bound stable as r grows, you absolutely must raise the exponent from 14 to 12.
That is the part that blows my mind, because there is no convoluted new gating mechanism being introduced here.
None at all.
They aren't bolting on like auxiliary losses to force the gradients to behave. They are literally just following the first order perturbation math to its logical conclusion and swapping a 4 for a 2.
It's remarkably elegant.
It really is. But like I said earlier, theory is just theory until it survives a GPU cluster.
Yeah.
So do they actually prove this holds up during a real pre-training run?
They did, and the controlled ablations they ran are highly revealing. They used GPT-style language modeling as their testing ground. Specifically, GPT-2 small at 124 million parameters and GPT-2 medium at 350 million parameters.
Okay, classic benchmarks.
Yeah. They trained these models from scratch on 50 billion tokens of the fine web edu dataset.
That's a solid run.
And it's worth noting that their baseline wasn't some weak straw man either. They compared DeepLoop against a model that already utilizes tied embeddings and input embedding RMS norm.
Good. So what happens when they just run it normally without any looping, like just standard depth?
At r equals 1, meaning no blocks are revisited, DeepLoop is essentially neutral compared to the baseline.
Like the validation loss curves are practically identical.
Yeah, practically identical.
Which actually makes perfect sense because at r equals 1, the tide depth effect doesn't exist yet. The runner is only doing one lap. The gradients haven't started aggregating.
Exactly. But the moment you turn on recurrent depth, when you set R to 3, 5, or 7 deep loop, consistently pulls ahead.
Really?
Yeah, it strictly improves the final validation loss across both the small and medium scales compared to the baseline.
Okay, loss curves are great.
Uh,
But how does it handle actual tasks?
yeah.
Because usually, if a model's internal representations are unstable, it just falls apart the second you ask it to do zero-shot reasoning.
The pre-training stability actually transfers beautifully. They use the Elm evaluation harness to test on 8 distinct downstream tasks.
Nice.
And at the R equals 7 loop count, Deep Loop beats the baseline on 7 out of those 8 tasks.
That's incredible. The jump on the Winogrand's reasoning task really stood out to me when I was reading. Winograndi is heavily dependent on common sense and pronoun resolution, which is tough.
It's notoriously tricky.
Yeah, and in the zero-shot setting, DeepLoop pushed accuracy up by 1.74 points. It went from 57.3 to 59.04.
Which is a very solid jump for a zero-shot evaluation.
Absolutely. But as impressive as those benchmark bumps are, the most fascinating part of the empirical proof, at least for me, was tucked away in Appendix C, the P-sweep experiment.
Oh, yes. The empirical P-sweep is where the physics of the neural network aligns just flawlessly with the theory.
So they fixed the loop count at R equals 3.
Correct. And then they systematically swept that scaling exponent, P, from 0.30 to 0.60 to just see what would happen.
Imagine being an ML engineer watching this run. When they set the exponent below 0.45, the models literally diverge. Like, they get stuck at what's called the unigram frequency floor.
It's painful to watch.
For anyone who hasn't experienced that particular flavor of pain, it means the compounding gradients have completely destroyed the model's representations.
Yes.
The model essentially brain damages itself and just spits out the most common tokens in the English language over and over again. Just an infinite screen of the word the and commas. It completely fails to learn.
But the moment the scaling exponent hits 0.50, training becomes reliably stable, the loss curve behaves, and the model actually learns real representations.
It's just such a stark phase transition.
It really is, and it challenges how we typically design hyperparameter searches. Very often in AI, we treat scaling factors as empirical knobs.
Right, you just twiddle them in a grid search until the loss curve looks right.
Exactly. But this P-sweep proves that P equals 12 is not just an arbitrary safe choice that happens to work by luck. It is the precise empirical phase boundary for training stability in aligned loops.
So the math predicted a strict boundary, and the training dynamics just perfectly validated it.
Perfectly.
Okay, so we have established that it works for standard language modeling, but let's be honest, standard autoregressive language modeling is just the baseline these days. The frontier of AI right now is heavily focused on complex reasoning architectures.
Yes, test time compute.
Right, we want models that can think longer before they output a token. So how does DeepLoop apply to architectures that aren't just a simple continuous loop, but instead have like complex inner and outer loops?
That's the real stress test. To figure that out, the researchers applied DeepLoop to the hierarchical reasoning model, or HRM.
The hierarchical reasoning model.
It's a brilliant test case because it introduces a hierarchy of recurrent modules executing at entirely different rates.
Right.
You have a high-level module that executes just one step, and then a low-level module that iterates many times within that single high-level step.
Oh, wow. Okay.
And on top of that structural complexity, HRM is trained using a one-step gradient approximation, which is a form of truncated backpropagation through time.
Okay, wait, let me stop you there, because that seems like it would throw a massive wrench into the m equals 2n calculation we talked about earlier.
It definitely complicates things.
Because truncated backprop usually means you run the full loop in the forward pass. But to save memory, you only calculate gradients for the very last outer cycle in the backward pass. So if the gradient isn't actually flowing through all the historical visits, how on earth do you calculate the stability bound?
That is the exact mathematical hurdle the authors had to clear. And they demonstrate that their framework gracefully extends to this truncated regime by replacing the total unrolled visit count with a gradient visible visit count. They denote this as M sub G.
Oh, I see. So they only count the visits the optimizer can actually see.
Correct. Because of the training truncation, the high-level module only contributes a single update term to the gradient. Functionally, it sits in the standard untied DeepNorm regime.
Right, it's just a single lap for that part of the model.
Exactly. But the inner low-level module is the engine that actually realizes the model's effective depth. It does this via aligned revisits at a fixed physical depth.
So it's running the laps.
Yes. Therefore, the inner module is what dictates the binding threshold for the entire architecture.
And because that inner module is looping and aggregating those gradients, that binding threshold remains exactly p equals 12.
Yes. It's the same mathematical bottleneck we saw in GPT-2, just localized to the inner reasoning loop.
That is fascinating. So what happened when they tested it?
When they applied this localized scaling rule to HRM, the results were highly significant. They evaluated it on ARC-AGI, which is notoriously one of the most difficult, logic-heavy reasoning benchmarks we currently have.
Yeah, it requires abstract visual reasoning that LLMs typically just really struggle with.
Right. And by doing nothing but applying the DeepLoop scaling rule, just swapping to p equals 12, the HRM's paper protocol two-vote accuracy jumped from 36.5% to 39.75%.
I want to push back on that for a second because, to a casual observer, a 3.25% bump doesn't sound like a revolution. Like, it sounds like someone might have just gotten a lucky random seed during evaluation. Why is a 3-point jump on ARC-AGI considered a big deal?
It is a massive deal because of how robust that benchmark is. A 3.25 percentage point gain on ARC-AGI represents roughly a 6 sigma effect statistically.
Oh, wow. Okay, so definitely not a random seed.
Not at all. It is incredibly difficult to move the needle on that specific dataset without fundamental improvements to the model's reasoning capability. It is a fundamental unlocking of the model's capacity to actually learn during those recursive inner loops without its internal states collapsing.
That makes sense. If the inner loop is unstable, asking the model to think harder just means asking it to compound its own errors faster.
Exactly. Which brings us to the ultimate thesis of the paper. Residual scaling must account for how depth is realized.
Right. It has to account for the actual parameter visits and their alignments, not just the nominal number of unrolled layers you claim on an architecture diagram.
It really forces you to rethink what a layer even is when you are dealing with recurrent compute.
It absolutely does.
So, wrapping this up, DeepLoop provides a deterministic, one-line conservative parameterization for post-layer normalization looped transformers. For anyone engineering test-time compute models, this is basically a fundamental building block now.
Definitely. You no longer have to guess the scaling factor or run expensive grid searches to find the stability boundary. The underlying math just dictates it for you.
It removes a massive empirical headache for ML engineers. You can confidently build these highly efficient, iterative reasoning models and know that your residual stream isn't going to explode just because you forced the model to think for 10 extra steps.
Right. The stability is mathematically baked into the initialization and the skip connections before you even launch the run. Which brings up a final thought for you, listener, to take away and mull over. So DeepLoop's p equals 12 exponent is necessary because it mathematically prepares the network for the absolute worst-case scenario.
Right, the conservative aligned regime.
Exactly, where the visit alignment coefficient, Kappa R, scales linearly with the loop count. The network basically has to assume the gradients from lap 1 are heavily correlated with the gradients from lap 5.
Because usually they are.
But what if we didn't have to assume that worst case? Like, could future architectures explicitly regularize their training to force decorrelated visits across loops?
That's an interesting idea.
Right. If researchers could somehow mathematically guarantee independent representations across loop iterations, we might safely be able to use less conservative exponents, like dipping back toward 14.
And that would squeeze even more expressivity and raw performance out of these recurrent models.
Exactly. It is a wild frontier for optimization. And honestly, it feels like we are just scratching the surface of what loops can actually do.